At the end of the last lecture, we were looking at the situation of horizontal plates. We considered a square plate or a rectangular plate or a circular plate held horizontally and losing heat either from its top surface or its bottom surface or from either side. We also considered a typical horizontal surface, and we said that if the surface is hot, then the fluid over it will try to rise in the form of a plume. Whereas the fluid below it will tend to stick to the surface, but will try to escape from the sides. The flow pattern will be different on the top surface and on the bottom surface. However, if the surface is cooler compared to the surroundings, then the fluid below the surface will become denser and will try to descend. So, this is the plume which moves down in this case, whereas the fluid near the top of such a surface will try to stick to the surface, will drift towards the edges and will try to escape downwards. In case of a heated surface, the general tendency of fluid surrounding the surface will be for moving up. In case of a cooled surface, the general tendency of the fluid surrounding it will be to move downwards. And because of this, we should appreciate that the situation of a heated surface facing upwards will be that of a heated surface of a cold surface facing downwards. And similarly, a cold surface facing upward will have a similar flow pattern compared to a hot surface facing downwards. Consequently, we expect to see two set of correlations, one for a hot surface facing upwards and one for a hot surface facing downwards. These two situations would be applicable respectively to a cold surface facing downwards and a cold surface facing upwards. Based on experimental data for such horizontal plate situation, useful correlations are provided by Macadams and by Lloyd and Moran. We should note that these provide average Nusselt numbers, not local ones. So, we have the average heat transfer coefficient. Properties are to be evaluated at the mean film temperature. One has to be careful about the characteristic dimension used in the dimensionless Grashof number or Rayleigh number, because it differs, definition of L differs for each shape of the plate, and it also depends on whether the plate is facing upwards or facing downwards. These are not valid for a very wide range of Prandtl number. The experiments have been done essentially with air, sometimes with water, and hence the correlations are expected to be valid for fluids with Prandtl number not far from unity. Air and water are okay, but they may not be valid for, say, liquid metals or for highly viscous oils. Let us first look at a correlation which is for a heated surface facing upwards or for a cooled surface facing downwards. These are similar situations. And you will notice that the Nusselt number is provided as a function of only the Rayleigh number. There is no separate existence of the Prandtl number. And for two ranges of Rayleigh number from 10⁻⁴ to 10⁻⁷, and from 10 raised to 7 to 10 raised to 10, we have Nusselt number as some constant into Rayleigh number raised to a small exponent. Notice that for these correlations, heated surface facing upwards or cooled surface facing downwards, the characteristic length L is defined as area of the surface of the plate of one side of the plate divided by its perimeter, and this is applicable for square plates, rectangular plates as well as for circular plates. You will notice that for a circular plate the characteristic length is not the diameter. For the other situation, a hot surface facing downwards or a cold surface facing upwards, we have a single range of Rayleigh number and a simple correlation similar to the earlier ones with a different value of the constant. Now see here, it is the L which is defined in a different way. For a square plate, it is side of the square. So if you have a square, say side A by A, then the characteristic dimension is A. Mean of two sides for a rectangular plate. If you have a rectangular plate, A by B, then L equals A plus B by 2. And if you have a circular plate, it is 0.9 times the diameter of the circular plate. Let us take an example so that we are exposed to solving problems with these correlations. The situation we are going to look at is this. We have a circular plate kept horizontal in still air. It is to be maintained at a surface temperature of 72 degrees C. The diameter of the plate is 0.3 meters. Either surface of the plate, top as well as bottom, has an emissivity of 0.6. The ambient air is at a temperature of 28 degrees C. Well, the plate is at some distance from the ground, and the ground temperature is 25 degrees C. And the top surface of the plate is exposed to the so-called sky, where you can say the temperature of the sky is 20 degrees C. Now the tape is warmer than the surrounding temperatures, and hence it will lose heat by natural convection and by radiation. Our task is to determine what is the heat loss from the plate. We will have to split this into 4 components, since it loses heat both by radiation as well as by convection, and both from the upper surface as well as from the lower surface. We can write 4 components. The total loss is from the top surface by radiation plus the bottom surface by radiation plus that from the top surface by convection plus that from the bottom surface by convection. Let us first calculate the area of the plate, which we will be needing again and again. This is pi by 4 d squared, which is pi by 4 into 0.3 squared, this turns out to be 0.070686 meters square. We'll use this again and again, so we'll calculate it once and finish it off. Let us compute the components one after another. Heat loss from the top by radiation. This will be sigma epsilon surface temperature raised to 4 minus sky temperature raised to 4 multiplied by area. This is 5.67 into 10 raised to minus 8, epsilon is 0.6. Now the surface temperature is 72 degrees C, which is 345 Kelvin raised to 4. Sky temperature is 20 degrees C, that will be 293 Kelvin raised to 4 multiplied by area 0.070686, and this turns out to be 16.34 watt, one component. Similarly, let us calculate the heat loss from the bottom by radiation. This will again be sigma epsilon, but now T surface raised to 4 minus T ground raised to 4 multiplied by area. Now between this expression and this expression, the only difference is T ground is 25 degrees C, which is 298 Kelvin, and if you substitute that, you will get this to be 15.10 watt. After having completed the task of obtaining the radiative components from the top surface and from the bottom surface, let us move on to compute Q top by convection and Q bottom by convection. For this, we will have to calculate Rayleigh number, and for calculating that we need properties at the mean film temperature, which is T surface plus T air divided by 2. Surface temperature is 72 plus 28 divided by 2, which is 50 degrees Celsius. If you read off properties of air at 50 degrees Celsius, you will get conductivity of 0.0283 watt per meter Kelvin. Nu is 17.95 into 10 raised to minus 6 meter square per second, and Prandtl number is 0.698. Now for determining the top heat transfer from the top by natural convection, we require, it's a circular plate, the definition of L here is area by perimeter. Area is pi by 4 d squared, perimeter is pi d. So we get diameter by 4. The characteristic length here is 0.075 meter. If you substitute these values in the definition of the Rayleigh number, G beta delta T L cube by nu squared into Prandtl number, you will get this to be 1.221 into 10 raised to minus 6. Remember, we need beta as a property, but then beta will be 1 divided by TMF in Kelvin, that will be 1 divided by 323 1 over Kelvin. So, we have everything here to compute the value of the Rayleigh number. After having computed the Rayleigh number, we use the correlation for the heat transfer from the top in that range, and that turns out to be Nu bar L is 0.54 into Rayleigh based on L raised to 1 by 4. Substituting our value of Rayleigh number, which is 1.221 into 10 to the 6, we will get this to be 17.95, which is H bar into L by K. Hence, H bar is 17.95 into K 0.0283 divided by characteristic length 0.075. This turns out to be 6.77 watt per meter squared Kelvin. And hence our heat loss from the top surface by convection turns out to be H bar into delta T into A, which is 6.77, delta T is 72 minus 28, and area is 0.07066, and this turns out to be 21.06 watt. Now we need to determine Q from the bottom by convection. For this, since it is a circular plate, L is defined to be 0.9 times diameter. So, this turns out to be 0.9 into 0.3, which is 0.27 meter. Notice that this is significantly different from that for the upper surface. This gives us a Rayleigh number to be 5.69 into 10 raised to 7. It is different because the characteristic length is different. All other components of the Rayleigh number remain the same. Now, using this Rayleigh number, we get by the correlation for the average Nusselt number, which is 0.27 Rayleigh number based on L raised to 1 by 4 is 23.46, which is H bar L by K. Hence, H bar turns out to be 23.46 multiplied by K 0.0283 divided by L, which is 0.27. This turns out to be 2.46 watt per meter squared Kelvin. and from which heat transfer from the bottom by natural convection is H bar A delta T, which turns out to be 7.65 watt. So, our total heat loss Q, which is Q from top by radiation plus Q from bottom by radiation plus Q from top by convection plus Q from bottom by convection. Let us write down these terms: 16.34 plus 15.10 plus 21.06 plus 7.65, everything in watts. Let us compute the sum of the radiative component and that of the convective component separately. So, radiative component total is 31.44 watts, convective component total is 28.71 watt. So, the total is 60.15 watt. And this indicates that in this situation the radiation is slightly more than half of the total heat loss. Radiation does not predominate, but it is as significant as natural convection, slightly more so. Now, let us look at the last situation, and that is enclosed spaces. Natural convection in enclosed spaces. And these enclosed spaces occur in many applications. Say a vertical enclosed space occurs between double glazed glass windows, common on air conditioned rooms. One side is at T1, another side is at T2. Sometimes they occur in horizontal situations. T1, T2. In solar collectors, we have a hot plate and which absorbs radiation, and there is a glass cover on top which suppresses convection. So, you have a gap, one surface is at T1, another surface is at T2. Depending on the orientation, whether it is vertical, horizontal or inclined, at some angle gamma from the horizontal, we will have different flow patterns. For example, in a typical inclined cavity where we have T1 and T2 as the two surfaces, and the remaining two surfaces, the smaller ones, are assumed to be insulated, the flow along the hot surface will move up. It will take some sort of a U-turn near the edges, will move down along the cooled surface and complete a circuit. Some sort of a circulation pattern will be set up. In case of inclined cavities, the circulation pattern is often a single circulation cell, whereas in case of horizontal cavities there will be a large number of small cavities formed known as Bénard cells. In case of a vertical thing, you may sometimes have a single cavity, sometimes single cell, sometimes multiple cells, depending on the ratio of the width L to the height H of the cavity. This situation is a very common situation in solar collectors, double glazed windows, and a number of applications of interest in industry, and hence it's a situation which is reasonably well studied both experimentally and analytically. Correlations are available for long cavities where the ratio of H by L is large, a cavity which does not look like a square but looks like a long rectangle. The recommended correlation is by Buchberg and Associates. It provides average Nusselt numbers. Properties are evaluated at T1 plus T2 by 2, where T1 is the hot surface, usually expected to be below the cooler surface, and T2 is the temperature of the cooler surface. So, the temperature difference delta T will be T1 minus T2. Properties are to be evaluated at T1 plus T2. It is valid for long cavity, that is H by L greater than 12, greater than or equal to 12. Since the data is essentially with air, it is expected that these are valid for Prandtl number near unity for air or for water. One correlation is valid for horizontal cavity and cavities inclined at approximately 67 degrees to 70 degrees. That is the range of the inclination of the Buchberg correlation. This upper limit of inclination is 67 degrees if H by L is 12 and 70 degrees if H by L is greater than 12. The correlation is in different ranges. If Rayleigh number into cosine gamma is less than 1708, the Nusselt number is 1, and this indicates that heat is transferred essentially by conduction. Then for different values of the parameter Rayleigh number into cosine of gamma, we have different correlations up to 5901, then up to 9.23 into 10 raised to 4 another, and up to 10 raised to 6 a third one. We will solve a problem based on this soon. For vertical cavities, there is a correlation by L. Sherbini and Associates. Again, it provides average Nusselt number for cavities with large aspect ratios. Typically, the aspect ratios are expected to be between 5 and 110. Again, Prandtl number is expected to be near unity. The range of Rayleigh number is from 10 raised to 2 to 2 into 10 raised to 7. And properties are evaluated again at the mean temperature T1 plus T2 by 2. Let's look at the correlation. Here there are three expressions provided for Nusselt number. Expression 1, which provides Nusselt number as a function of Rayleigh number. A second expression again providing Nusselt number as a function of Rayleigh number, a more complicated one. And a third one, though simple, but it provides Nusselt number as a function of Rayleigh number and the aspect ratio H by L. And we have to select the maximum of the three values of Nusselt number obtained by using these three correlations. So, we must calculate, say, Nu bar L1, Nu bar L2 and Nu bar L3 and select the maximum of these as the average Nusselt number. Now, the earlier correlation by Buchberg gave us correlation or Nusselt number up to an inclination of about 70 degrees. So, from horizontal to approximately 70 degrees, we have the Buchberg correlation. For vertical, we have the L-Sherbini correlation. So, for angles between 70 degrees and the vertical, it turns out that we can use the Nusselt number determined for the vertical correlation and multiply it by the fourth root of cos alpha, where alpha is the inclination with respect to the vertical. So, alpha will actually be 90 degrees minus gamma. So, with this the L-Sherbini correlation and the Buchberg correlation provide us almost all cases for horizontal, inclined and vertical cavities. Let us solve an example. Let us say that we have a cavity which is part of a solar collector. Let us say it is inclined at some angle gamma. We will obtain solutions for some different values of gamma. This is the collector plate which is at 75 degrees Celsius, and the glass surface is at 55 degrees Celsius. The inclined height of the collector H is 1 meter, and the gap between the absorber plate of the collector and the glass is 2.5 centimeter. The width of the collector, say perpendicular to the plane of the picture, is 2 meters. So, the collector area will be 1 meter by 2 meters, 2 square meters. And we would like to determine what is the heat loss from the hot surface to the cold surface Q for different values of gamma. Let us try to cover as much of the range from 0 degrees to 90 degrees as possible. We will have to determine the mean film temperature, that is T1 plus T2 by 2, which is 65 degrees C, which is 338 K. To begin with, we will neglect radiation. In the comparison, we will assume radiation doesn't take a part. However, we should notice that radiation will not be depending on the inclination of the surface. So, finally, we will determine a value for the radiative component. At this temperature, let us determine properties of air. Conductivity 0.0294 watt per meter Kelvin. Prandtl number is 0.695. Kinematic viscosity 19.50 into 10 raised to minus 6 meters square per second. Beta is 1 over 338 per Kelvin. Let us calculate the Rayleigh number, RAL. This is G beta delta T L cube by nu squared into Prandtl number. We know everything here. Value of G is assumed to be 9.81 meters per second per second. This turns out to be 1.6577 into 10 raised to 4. This is greater than 1708, so there will be natural convection in the gap. Let us compute at gamma equal to 0 degree. So, horizontal. In this case, Rayleigh number into cosine gamma is 1. So, this is 1.6577 into 10 raised to 4. We have a correlation for the average Nusselt number, which is 0.229 RAL cosine gamma raised to 0.252, and this turns out to be 2.649, and hence the average heat transfer coefficient, which is Nu bar L into K by L, this turns out to be 3.12 watt per meter squared Kelvin, and the heat flow rate will be H bar into A into delta T. H bar is just computed, area is 2 square meters, delta T is 75 minus 55, which is 20 degrees Celsius. This turns out to be 124.6 watt. Proceeding in the same way, one can calculate at different values of gamma. For example, at gamma is 15 degrees, you will get the heat loss to be 123.5 watt, only slightly smaller than the 124.6 watt which we obtained just now. Gamma equal to 30 degrees, we will obtain 120.2 watt. Gamma equal to 45 degree, we will obtain 114.2 watt. Notice that up to 45 degrees there isn't any significant decrease in the amount of heat loss. At 60 degrees, Q is 104.6 watt. Since H by L is 1 meter divided by 0.025 meters, which is 40. Our gamma star, the limit for inclination for use of the Buchberg correlation, is 70 degrees. And at that, let us calculate Q, and that turns out to be 94.6 watt. So, from horizontal to the inclination of 70 degrees, the heat loss reduces from about 125 watt to about 95 watt. Okay, a decrease of around 25%. Now let's look at the other end. Gamma equals 90 degrees or alpha equals 0 degrees, and that is vertical orientation. In this we have three correlations, and we have to determine the maximum of the three, Nu bar L1, Nu bar L2 and Nu bar L3. And if you do that, you will get from the first correlation the value of the Nusselt number to be 1.542. From the second correlation, you will get 1.563, and from the third correlation you will get 1.246. We select the highest of the three. So this is the Nusselt number, which gives us an average heat transfer coefficient of 1.83 watt per meter squared Kelvin and a heat loss of 73.5 watt. And using the inclination relation at 75 degree, which means alpha is 15 degrees, we obtain Q equal to 72.9 watt. So if you tabulate the results, you will notice the following. We'll say gamma in degrees and Q in watt. We have result for 0 degrees, 15, 30, 45, 60, 70, 75 and 90. 124.6, 123.5, 120.2, 114.2, 104.6, 94.6, 72.9 and 73.5. So we get the highest heat loss when the cavity is horizontal, reduces to about 72, 73 watts when it is 75 degrees, increases slightly to 73.5 watts. How does this compare with radiation? Remember, in any natural convection situation, radiation plays a dominant role. So let us assume that for the plate surface the emissivity is 1, for the glass surface also the emissivity and absorptivity are 1. For the glass surface this is a good assumption. For the plate surface this is not that good an assumption, this will typically be 0.8. However, assuming 1 will give us the highest value of radiative heat transfer. So assuming this, our heat loss from the absorber plate to the glass surface by radiation turns out to be sigma A T1 raised to 4 minus T2 raised to 4, and this turns out to be 350 watt. Even if the emissivities were slightly lower, for example, this would be 1. If this is 0.5, even then this is 175 watt. And that means in this situation, whatever be the inclination, the radiation is going to dominate the natural convection. Now that brings us back to the end of the study of natural convection. What we did in this set of lectures for natural convection, so we looked at natural convection as a phenomena. We looked at the dimensionless numbers. Particularly the numbers for importance for us are Grashof number and related to it the Rayleigh number. Then we looked at correlations, and the situations we looked at were vertical plate, horizontal cylinder, then horizontal flat plates, both facing upwards as well as facing downwards, and finally enclosed spaces. We looked at correlations and we solved problems using these correlations. We noticed that in a large number of situations of natural convection, radiation dominates. So, whenever you solve a problem in natural convection, in any situation, use the proper natural convection correlation, obtain the natural convection heat transfer, but simultaneously also compute or estimate the amount of heat transfer by radiation, because in natural convection that will play an important role. Thank you very much.